Hey folks, so going back to where we left off in the previous video, we established that we've collected our data points, xi to xn, and we want to fit this yellow normal distribution and guess a value for mu such that all of our likelihoods of having seen these data points, so this green point times this green point times this green point times this green point, that this is maximized, that that's as high as possible. So we have that the probability of having seen our data is the likelihood of having seen all the individual data points, right? So px1 times px2 all the way to pxn. And what are these actual probabilities? Well, that's given by this expression here. So I've taken the probability density function of the normal distribution from Wikipedia, and this part that I've outlined in yellow is just the equation of this yellow line here. So I can rewrite this as the product of I going from 1 to n of 1 over 2 pi sigma squared, looks like a 6, sigma squared, okay, e times e to the power of negative xi minus mu squared over 2 sigma squared, right? Okay, so I've just substituted my individual xi's in for the x here, and I'm taking the product of all of them. Okay, great. So this is the likelihood of having seen our data, and if we want to maximize this likelihood, we can just take the derivative of this whole thing and set it to 0, right? So easy. Well, not quite. This math is a little bit hairy to deal with. We have to use chain rule across all these products. It's not super pretty. So let's use these useful facts here at the side to make our life easier. So the first is that the natural logarithm of e to the x gives us x. So, maybe we can use that to address this exponential here. Also, we have the natural logarithm of a times b is the same thing as the logarithm of a plus the logarithm of b. So we can take the logarithm of a product and change that into a sum of the individual logarithms. Also very useful. And lastly, logarithm is a strictly increasing function. So if we have a larger than b, then the logarithm of a is larger than the logarithm of b, meaning that if we maximize the logarithm of our likelihood, we have also maximized our likelihood. So let's go ahead and do that instead. I'm going to take the natural logarithm of our likelihood, and that's going to be, well, remember we have here a logarithm of product is sum of logarithms, so we can change this to sigma, right? And then we have the logarithm of all the stuff up here, right? 1 over square root of 2 pi sigma squared, and then e to the negative xi minus mu squared over 2 sigma squared. Okay, so now we have this. Cool. So let's break this up a little more, right? We have our sigma. So realize here we have another logarithm of products, right? So we have this times this, so that's going to be logarithm of, I'm going to write the e out here first, e to the negative xi minus mu squared over 2 sigma squared, and then I'm going to add logarithm of 1 over 2 pi sigma squared. Okay, right, because this is the product of these two things, so I've broken them up into a sum again. And then this simplifies to, well, logarithm of e to the thing is just thing, right? So this is negative xi minus mu squared. And I'm actually going to write this 1 over 2 sigma squared out separately here. And then I'm adding, this is just going to be some constant, right? For the purpose of maximizing with respect to mu, all of this is constant. You notice that mu doesn't appear in here at all. So I'm just going to write constant here, whatever that value is. Okay, so that's our log likelihood. And now I want to take the derivative of this whole thing and set it to 0, right? So the derivative of the natural logarithm with respect to mu is going to be sum, right? Sum of derivative is the same thing as derivative of sum. So I've got my negative 1 here, right? I've got my xi minus mu, and then I'm taking the derivative, so that drops down to a 1, multiply it by 2, and then chain rule on the inside. We've got our negative 1, right, from the negative mu here. And then that whole thing is still multiplied by 1 over 2 sigma squared. And the derivative of this constant with respect to mu is just 0, right? So I've got my 0 here. So that drops out. Okay, so now let's simplify this a little more. We've got sigma, negative 1 times negative 1, those cancel. So I've got the 2 and the 2, those cancel. So I've got my xi minus mu, and then 1 over sigma squared. And I want to set this whole thing equal to 0. And sorry, that's the sigma. Okay, So first thing to notice is that if we're trying to set this equal to 0, we have to either set this part equal to 0 or this part equal to 0. We can't set this equal to 0 because that's a constant, so we're just going to disregard this, right? For the purpose of making our derivative equal 0, it has to be the case that 0 equals this part here. This is the only way we can set that equal to 0, right? I'm going to kind of disregard this because there's nothing we can do about that constant. So how do we simplify this further? Well, 0 equals the sum of, I can't simplify sum of xi's, right? All the different xi's are different, so I have to leave this as a summation for I going from 1 to n. All of these were I from 1 to n. We're just, getting a little lazy. But the sum of mu, which is a constant, right? Mu is the true population mean, and it exists out there somewhere. We'll never know what it is because we can't measure everybody, but it is a constant that's out there. The sum of that from I going to 1 to n, well, that's just going to be n times mu. Right? So 0 equals the sum of this minus n times mu. Or, in other words, n times mu must equal the sum of xi from I going from 1 to n. So now you can probably see it, right? We divide both sides out by n, and then we end up with mu equals sigma xi from I going from 1 to n divided by n. That gives us our best guess for mu. This is the guess for mu that maximizes the likelihood of us having seen all of those data points. And as you can see, this is just our common sense definition of the average, right? We add everything up and we divided it by the number of things that we have. So that's sort of the formal proof for the maximum likelihood estimator for mu. But I hope it was helpful for you to see the intuition behind what it actually means to, put a maximum likelihood estimator on a set of data and why that corresponds to our intuitive definition of the average. And in the next video, we'll go into doing this exercise again, but we'll do it with respect to sigma squared, which is the variance. And we'll prove that the maximum likelihood estimator for variance is the sum of xi minus mu squared over the number of things that we have. So yeah, I will see you in the next video.